Hey everybody, today we're going to be talking about a new type of transformation called rotations. Should be a real hoot. Rotation is a transformation that turns about a fixed figure called the center of rotation, okay? In this picture, point P is the center of rotation. The angle measure of the rotation is called the angle of rotation. So in the diagram, you see that triangle QPR, that is the black pre-image, is rotated 90 degrees about the center of rotation, point P. Notice that the angle of angle QPQ prime is 90 degrees. That's why it's a rotation of 90 degrees. Notice also that it's moving to the left or counterclockwise. That's significant here. The direction of a rotation is always going to be counterclockwise in this book. What you see here are two different illustrations of something being rotated 90 degrees. We have triangle BCD that is rotated 90 degrees about the origin to triangle B prime, C prime, D prime. I want to really look deep into this and see if we can notice any sort of connections between the points of the original pre-image and what happens after we rotate it. First of all, take a look at the points of the pre-image, triangle BCD, and notice their coordinates. B is 2, -1, C is 5, 2, and D is 6, -1. Now I'm going to rotate it 90 degrees. Okay, so these are the coordinates of the image. B prime is 1, 2. C prime is -2, 5. And D prime is 1, 6. I really want you to look at the connection between the original points and the primes. Something really interesting going on there. So I want you to start thinking of some hypotheses. And while you're doing that, let's look at our second figure and see if we can do the same kind of thing. It might help trying to figure out what is actually going on here. Okay, so first of all, I have written down the coordinates of the points in the pre-image, which is quadrilateral BCDE. And you can see the coordinates are 2, 2 for B, -5, 1 for C, -5, 3 for D, and -4, 4 for E. Now we're going to rotate that 90 degrees as you see in the illustration. Remember, this is a 90-degree rotation, which is counterclockwise around the origin, which is point A in this case. So take a look right there. It's around that point. Now I'm going to give you the coordinates of the image. Okay, and now here are the points of the image. So B prime, C prime, D prime, and E prime, which you can see I didn't write in. What is going on here? There's a really interesting connection between the pre-images and the images that is true in every single one of the points that you see anytime I rotate 90 degrees about the origin. I want you to take a minute to write down your hypothesis, maybe even pause the video, and when you're ready, I'm going to move on. Okay, so I'm hoping you can see that in each instant, what I did was I took the original X and Y values and switched their positions. But not only did I switch their positions, I changed the sign of the original Y value. So for example, if you look at C and C prime, the original Y value in point C was 1. The coordinates were -5, 1. Then I switched those two numbers' positions, but now the 1 became -1. Using arrow notation, we would write that this way, that if we start with X, Y, we end up with switching the positions and changing the sign of Y, so we get -Y, and then the X just takes the other position. So this is arrow notation for how to write a 90 degrees rotation counterclockwise. X, Y becomes -Y, X. Now here we are with two illustrations of a 180-degree rotation about the origin. You can see that they're kind of on the opposite sides from each other. They look a little bit like a reflection, like we did yesterday, but it's not exactly the same. Something else is going on here. So I'm going to write down all of the pre-image points for both figures, and then all of the image points, and see if we can make a similar kind of connection as we did before. So next, just take a gander, if you will, at the pre-image points for each of the figures. Make sure you can actually tell what I'm talking about. Look at the pre-image in each figure. Look at the coordinates that I wrote down, and see if you agree with them. Now I'm going to write down all the coordinates of the images, the things that I get after the rotations. Let's kind of check out what sort of mad thing happens here, my friends. Okay, now very well, my brothers and sisters. What is it you see? What magnificent thing has transpired between the pre-image and the image in each of our situations here? Take a second and pause the video. Just look them over. I think you'll find something pretty interesting. All right, I'm pretty sure you figured this one out. If you look really closely, you're going to see that all that happened was that the original coordinates just changed their signs. So whatever x was, it became the opposite, or we could write that as negative x. Whatever the original y value was in the pre-image, in the image, it just became the opposite of that. So if we start with points x comma y, the arrow notation would be we do negative x and negative y, which just means the opposite of what the x was and the opposite of what the y was. All right, so now let's actually just try to do this by taking a figure such as triangle ABC, as you see here, taking down its coordinates, and then applying the arrow notation to make the transformation of a rotation of 180 degrees about the origin. We just learned how to do it. I'm gonna ask you to try to copy this picture down to the best of your ability in your notebook while you pause the video, and then try to calculate what the new points are, and then draw them, and then see how you did. So first, we write down the original points. A would be negative 5 comma 1, B would be negative 4 comma 2, and C would be negative 3 comma negative 1. Once we have that, we just have to apply the transformation. If you look back at the arrow notation that we came up with, it should be pretty easy to figure out. The first thing you had to recall what the arrow notation was. If we start with points x comma y, our new points will simply be the opposite of x and the opposite of y, which is what you can see I've done here. Since A was negative 5, 1, A prime would be 5 comma negative 1, and so on. Our next step would then be to graph those three new points. 5 comma negative 1 is A prime, 4 comma negative 2 is B prime, and 3 comma positive 1 is C prime. And finally, we just connect those lines to make the new triangle, the image of triangle ABC. And voila, ici, here it is, our delightful, delicious new triangle, A prime, B prime, C prime. Isn't it beautiful? Rotated a nice, nifty 180 degrees about the origin. I knew you'd think so. It is quite a delight. Well then, my friends, how about a 90-degree rotation? Same triangle, different rotation. Just to get you started, first, write down the original points. Next, figure out, by looking back, what is the transformation using arrow notation? Find the new points, graph them, and connect them. Okay, well, I've kind of fast forwarded here. First, I took the original coordinates, which are the exact same as the previous problem, and then I remembered my arrow notation was that if I have my original figures, x, y, I simply switch the position of x and y and then change the sign of y, which is what I did in each of the prime here, A prime, B prime, and C prime. After doing that, I plot the new points, I label them, and I connect them to make the transformed triangle, A prime, B prime, C prime. Wow, beautiful stuff. Okay, so something else about rotations is something called rotational symmetry. A figure has rotational symmetry if you can rotate it 180 degrees or less so that the image exactly matches the original, as like you couldn't tell that you'd actually spun it, all right? This book talks about rotations happening in counterclockwise fashion, okay? So what you can see here in this figure is that if I were to rotate this amount of degrees, okay, which we'll talk about in a second what that is, it's gonna look exactly the same as it did before. And as a matter of fact, I could do this 5 times with this particular figure before I got back to the original position, okay? Because every time I spun it that amount of degrees, it would look like the original. So 72 more degrees looks exactly the same. 72 more looks exactly the same. 72 more looks exactly the same. And then finally, I get back home again and it looks exactly the same. So there's 5 different times that happens. 1, 2, 3, 4, 5. This is said to have 5 rotational symmetries. And the simple math here is if you want to figure out what is called the angle of rotation, or which is the smallest amount that it will take to make it look exactly like itself, you simply say, how many rotational symmetries does it have? 5. And divide by 360 by that number. 360 divided by 5 is 72 degrees. That is the angle of rotation of this figure, okay? 72 degrees. Every 72 degrees, this figure will look exactly like it did. And you can do it 5 times in a rotation between 0 and 360. Another quick example. Here we have this flower that's sort of triangular, and you can see that you could do this 3 times. Here, here, and then back home again. So there's 3 rotational symmetries in this figure. So 360 divided by 3 is 120 degrees. So just like we said before, this figure has rotational symmetry, and the angle of rotation is 120 degrees. Now I want you to take a look at this figure, do the best you can to figure out how many rotational symmetries this puppy has. How many does it have? And use that number to determine what is the angle of rotation, which is the smallest number of degrees you have to turn it so that it looks exactly like itself. Okay, so here it is done out. I just chose a specific point on it, and I can rotate 6 times so that it looks exactly like itself. And so 360 divided by 6 is 60 degrees. So this has 6 rotational symmetries, and the angle of rotation is 60 degrees. Let's take a look at one more. All right, so same thing. Take a look at the picture, count the number of rotational symmetries, and use that to figure out the angle of rotation. And please, pause the video for a moment, try it out on your own before you continue. All right, so once again, this has 9 rotational symmetries. I can spin this 9 different ways to make it look like itself in a full rotation. So it has 9 rotational symmetries, and 360 divided by 9 is 40. So the angle of rotation is 40 degrees. Okay, so last thing we're going to do is we're going to try to do a little bit of work on the GeoGebra Classic. Showed you yesterday in class how to get here. I'm going to show you how we can use it to make rotations around the origin of different amounts than 90 degrees or 180 degrees. Okay, so first we're going to draw a triangle somewhere. Any triangle. I'm showing you how. You can pause the video several times and rewatch this part if you need to. But I'm just going to make a random triangle using this tool. Okay. And then using the point tool, which is right here, I'm going to make a point right at the origin. And then what I'm going to do is I'm going to do a rotation. Rotations are under the same tool as the reflections were. So I click here and it says rotate around a point. So I click that. Now you might see on the bottom it says select the object to rotate and the center point and then the angle. So first I click on the triangle and then I click on the point that I made at the origin. And it's set for counterclockwise. So I change this to 270 degrees and I hit OK. And now that has been rotated 270 degrees counterclockwise. And that is all I'm going to ask you to do as part of your homework. Hope you've enjoyed our lesson today. If you have any questions, send me an email.